All right, here we're going to look at question 4 on the worksheet that says to consider the region R, which is the set of all polar coordinates r theta, where r varies from a to 1 and theta varies from 0 to pi over 2. Okay, so I've gone ahead and sketched a picture of the region R up here, and you see that this is the region bounded by these two quarter circles in the first quadrant. So it's this quarter annulus here. And our job in part A is to find the centroid of this region. And then it says, note that your answer will depend on A, this inner radius here. All right, so recall that when talking about a centroid, the assumption there is that the mass density is uniform. Okay, so to go ahead and compute the things we're going to need, well, for our mass calculation, I'm just going to be integrating our density function over this region. And there I'm just going to be integrating a constant over the region. So that's going to be that constant k times the area of the region. And since I have this quarter annulus shape, that area can just be found using pi r squared. And then I'm going to wind up having to divide by 4 because I just want this quarter annular region. So I get pi over 4 times the quantity 1 minus a squared for the area, and then there's that factor of k from the density. Okay, then for the moments, well, for the y moment, I'm going to have the integral of x times our density function over our region. And in polar coordinates, our radial value r will vary from a to 1. And then we're going to sweep from theta equals 0 to theta equals pi over 2. So we're going to sweep through that first quadrant. And x in polar is r cos theta, our density is k, and our differential area element dA is r dr d theta. So go ahead and compute that integral. You'll wind up getting k over 3 times the quantity 1 minus a cubed, which then will imply that the x-coordinate of the center of mass, so x bar, would be this y moment divided by the mass. So take this expression for the y moment, divide by the mass that we computed up here, and you wind up getting this expression 4 over 3 pi times the quantity 1 minus a cubed all over 1 minus a squared. Okay, now for the x moment, pretty similar. Now we're going to integrate y times the density over the region R, and y in polar is r sine theta. And so when you go ahead and compute this integral, you wind up getting this same quantity. And now for y bar, you're going to take that x moment and divide it by the mass, and we wind up getting, well, the same coordinate as we got up here for x bar. And what that's implying is that our center of mass is going to lie along this diagonal y equals x. And given this shape here and the fact that it's symmetric about that diagonal, and we're assuming uniform density, that makes a lot of sense. All right, so we conclude that our centroid is given by this location. And now part B says to sketch the region R and label its center of mass when A is equal to 0.5 and when A is equal to 0.9. What do you notice? All right, so when A is 0.5, okay, our center of mass here, if I just plug in 0.5 into this expression, is about 0.495, comma 0.495. Okay, so now if I measure the distance from this point to the origin, well, since it lies along this diagonal y equals x, that distance would just be 0.495 times the square root of 2, and you'll get a number that's a little bit bigger than zero point 0.5, which implies that our center of mass in this scenario, when a is a half, lies inside of our region. Okay, so now what if we set a to equal 0.9? Well, there, again, just plugging in 0.9 into our expressions up here for the centroid, we get the centroid's located at about 0.605, comma 0.605. And now the distance from this point to the origin would be 0.605 times the square root of 2, and that gives you a number slightly less than this inner radial value of 0.9. And that implies that our center of mass, in fact, lies outside of our region. Okay, so now I've noted previously that this interpretation of the center of mass is just this balance point. Okay, while it does lead to a good physical interpretation of what center of mass is all about, the thing though you have to be a little bit careful about is the fact that in scenarios like this, where the center of mass in fact does not lie in the region, so if I were to draw a picture here, okay, well, if I try to balance my region here at this point, of course, it's not going to balance at all. In fact, it's not even touching the region, right? So it's just going to fall straight to the ground. So what do I make of that? Well, one thing you can, of course, say, even though this center of mass does lie outside the region, is remember in terms of the moment interpretation, if I were to concentrate all of the mass of my region at this location, okay, the moment of that new point mass, okay, about the x-axis and about the y-axis, so those rotational tendencies would be the same as this original region. Okay, so there is still that interpretation. Uh, but now going back though to the balance interpretation, we can still actually, in a certain sense, treat this as the balance point if you say allow some kind of connective tissue between our region and this location. So in other words, if I take, say, like a really, really thin wire whose mass is just negligible when compared to the mass of our region, and I connect our region to this location, then this thing will balance. Okay, and a classic example to illustrate this very thing is this balancing forks magic trick. Okay, this is a video that Harvard put out to kind of bring home this point of an instance where the centroid lies outside of the region. I'll post a link to the video. You can see that they've attached a matchstick here to the corkscrew, and they actually light that match with a blowtorch for some nice theatrical flair. But in any event, right, this this sort of thing, of course, can happen precisely because of the fact that in certain instances, the center of mass just does not lie within the region. All right, that's going to do it. Thanks so much.